Imagine the universe like a grand symphony, but instead of musical notes, the universe is composed of tiny, vibrating strings. These strings are so small that they are beyond our current ability to see them. Yet, string theory proposed that these vibrating strings are the fundamental building blocks of everything. Around us, every particle, every force, even space and time themselves arises from the music of these cosmic strings. Just like different vibrations of a violin string produce different musical notes, different vibrations of these cosmic strings create the different particles that we observe. An electron is one note on a string, while a quark is another. The entire universe in this view is a symphony played out on an unimaginably small scale. This idea, while mind-boggling, offers an elegant and potentially revolutionary way to understand the universe and everything in it. It could be the key to unlocking some of the craziest mysteries in physics. For centuries, physicists have striven to understand the universe through the lens of physical laws. Two of the most successful frameworks we have are Einstein's theory of general relativity and quantum mechanics. General relativity describes the universe on the largest scales, stars, galaxies, and the fabric of spacetime itself. It explains gravity as the curvature of this fabric of spacetime. Quantum mechanics, on the other hand, governs the physics of the really small, including small atoms, subatomic particles, and their interactions. It reveals a world governed by chance and uncertainty, where particles can behave like waves, probabilistic waves. Here's the problem. These two pillars of modern physics seem fundamentally incompatible. They offer conflicting descriptions of reality, especially when it comes to extreme environments like black holes or the very beginning of the universe. This clash suggests that our understanding is incomplete and that a deeper theory is needed to reconcile these two giants. String theory steps in to offer a possible resolution. It proposes that the universe is not made of point-like particles, but of tiny, one-dimensional vibrating strings. Imagine these strings as incredibly small rubber bands, far smaller than even the smallest particles we know. Each string can vibrate in different ways, and each vibration corresponds to a different type of particle. But there's a catch for string theory. To work mathematically, our universe cannot be limited to the 3 spatial dimensions and 1 time dimension that we experience. Instead, it requires at least 10 dimensions. These extra dimensions are not some far-off realm. String theory suggests that they are curled up and hidden within the fabric of spacetime, too small for us to perceive directly. While the idea of extra dimensions might seem strange, it provides the framework for string theory to potentially unify and reconcile quantum mechanics and general relativity. In the quest for the theory of everything, physicists are drawn to string theory specifically because it holds the promise of a theory of everything, a single elegant framework that explains all the fundamental forces and particles in the universe. The quest to find the cosmic code, the ultimate set of rules governing reality. Imagine that a single equation could describe the birth of a star, or the glow of a firefly, or maybe even the spin of an electron, all stemming from the same fundamental principle. We're really looking for an inch-long equation such as E equals mc squared. It doesn't have to be that small, but
That's what she said.
any equation, single equation that could govern the entire universe would explain so much. Using the vibration of these so-called strings is a dream of string theory, to do exactly that, to reveal a hidden symphony that orchestrates the cosmos. If successful, string theory could answer some of the most profound questions about the universe. What happened before the Big Bang, maybe? What lies at the center of a black hole? Or maybe what is the true nature of space and time? String theory could help us answer all these questions. Why do physicists care? I mean, like I said, string theory might unify all the forces of nature. Gravity, electromagnetism, the weak and strong nuclear forces, all of these in one beautiful framework. Also predicts gravitons, the theoretical particles of gravity, and gives us tools to understand black holes, the early universe, and even weird concepts like holographic universes and multiverses. But here's the catch. String theory hasn't been proven, and not even close. We don't have experiments yet that can test it directly. So where does that leave us? String theory is one of the most ambitious ideas in physics, but also one of the most controversial. Some scientists love it, some say it's untestable, even unscientific. But whether it's right or wrong, it's pushed physics into new creative direction. And who knows, Maybe one day we'll finally find a way to peek into these hidden dimensions. For now, string theory remains the universe's most beautiful maybe. Want to go deeper into this theoretical rabbit hole? Hit that like button, subscribe, and stay tuned for more physics videos such as this one. Because out here in this universe, sometimes there are strings attached. Don't forget to like and subscribe. It's free, and you can change your mind at any point in time, and it really helps me out as well.